Okay. Okay. So this is the Bode plot of a transfer function GS, and it has been told that the Bode magnitude plot has a value 32 when omega is 1 radian per second, and has a value of minus of 8 when omega is 10 radian per second. It has been, that is what has been written in the statement over here, and it has been told that the phase is negative for all values of the frequencies, and you are asked to find the transfer function g of s. So the options are given to you. I would ask you to solve the question, try the question for yourself. I will give you 3 minutes time to do it. It is 7-4. I will be asking at 7-7. So try the sum. If anybody solves the problem before time, they can just unmute themselves and just tell what answer they are getting. Anybody with the answer yet?
No, sir.
I think your time is up. So is anybody there who has solved it?
No, sir.
Anu, have you solved it? Navkirti, what is the problem that you are facing in this question? It is a
Sir,
simple question. Yes.
I just tried to
Try to.
find the slope because
Yes.
that's how I can just determine whether it's S or S square, and that's where I'm
Yes.
having
Yes.
problem.
So how are you finding the slope?
Sir, as given 20 log j of s is equal to 32, and other minus 8 dB. So from that equation, but there I'm stuck.
So what slope are you getting?
Actually, sir, I was unable to solve. I just
Okay. So so do you know what logarithmic scale is?
yes, sir.
So what does that mean?
So
This
in decades, 1 200 like increasing 10 raised to power.
10 raised to the power 1, right? So you see the omega over here, it is the first unit is 1, the second is 10, the third unit is
So 10 raised to power 1 to
100, right? So
100.
it is increasing by 10 times. So so why is it called a logarithmic scale? Why would I say that if it increases by 10 times it is a logarithmic scale? Any idea, Navkirti?
So we just say that
No,
when
there must be a
the
reason
scale
why
is
we say
increasing by decade.
no. Decay is a different thing. Decay is we are talking about the slope, decayed and all those things. They're talking about the slope. I'm
Yes,
talking
sir.
about yeah. I'm talking about why am I saying that when the omega is increasing by 10 in each unit, it is called a logarithmic scale. Why am I saying that? Is there any reason why I'm saying that?
So because it can just cover large scale.
No, that is the reason. That is the reason why why we are doing a logarithmic scale. There are several reasons. So the main reason is to make the Bode the Bode plot linear. Uh, the x-axis is considered a the x-axis is in logarithmic scale to make the Bode plot linear. That is the reason for uh, taking a logarithmic scale. But that is not what I am asking. I am asking why do we say that increasing by 10 units means logarithmic scale?
So because log base to 10, maybe something related to that.
Okay, so in a graph, so when you are say a simple graph, if it is a linear scale, if I consider, so if this point is 1, what would be the next point? Say we are increasing by 1 unit. Okay, we're increasing by 1 unit. So the next point would be 2, right?
Yes, sir.
Then another point would be 3,
Yes, sir.
and then it will be increasing accordingly. So what is the amount but by which you are increasing?
By
By
unit
unity.
1.
By unity, right? By unity you are increasing.
Yes, sir.
So log of 10 is what?
So
Log of 10 is what is the value of log of 10?
I forgot.
So log base 10 of log of 10 base 10 is 1, right?
Okay, sir.
So that so do you understand that by increasing omega by 10 times in logarithmic scale we are increasing by 1 unit.
Okay, sir.
Log of 10 is 1. So I have increased logarithmic scale by 1 unit. Log of 100 is 2. So we are increasing again by another unit.
Yes, sir.
Getting my point?
Yes, sir. Got it.
Okay, so that is what we call a logarithmic scale. So, so it can also increase. So there you may have seen some octave. In octave, you would find that the omega is increasing by 2 times. So if it is 2, then 4, then 8. So this fashion, it would be increasing by 2 times. Okay, so that is also a logarithmic scale. So now let us move ahead and see how to solve this sum. Okay, the first thing is, as you have already told, to find the slope of the line that has been given to us in the question. How would you do that? 32 is the value of this. What is the value of frequency at this point? That is unity. The value of this straight line at omega equal to 10 radian per second is minus 8, right? And what is the value of omega at that point? That is 10. So how do you find the slope? So you have to consider that this is not a linear scale, this is a logarithmic scale. So if you do that, see 32 is this value. And what is the value of frequency at this point? That is log of 1. As I have told that when omega is 1 radian per second, the value of the straight line is 32. minus of this value, minus 8, because you have been told that at omega equal to 10 radian per second, the value of this magnitude plot is minus 8. So 32 minus of minus 8 divided by log of 1, that is this omega, minus of this omega, because this is the value of omega for which the curve has a value minus 8. So if you do that, what you are getting minus 40 dB per decade. Do you see how to find the slope of the curve?
Yes, yes, sir. While I was solving other questions, I was getting stuck in these kind of equations.
Okay, so are you clear with the concept now?
Yes, sir.
This concept is clear now, how you have to find the slope?
Yes, sir.
Okay, so now just I have told before ki why is this, what is the reason behind plotting the omega axis in logarithmic scale. You would see it over here. You see it is a straight line, okay, but you see the relation of gs. So look at the relations over here. These are not linear, right? These, none of this relation are linear. These are not straight line equations. Are these straight line equations? If you write mod of g of omega, that is 39.8 by omega square. So is that a straight line equation? It is not a straight line equation, right? It is a parabolic equation, right? Getting my
Yes,
point?
yes, sir.
What I'm saying is, if you look at, if you forget about log 20 log thing, just look at g of s. So if it is 39.8 by s, that is, you replace s by j omega and then you take mod of g of j omega, that is 39.8 by omega. So that is not an equation of straight line, right?
Yes, sir.
So that is something which is not linear. The equation is not a linear equation. It is not an equation of a straight line. Correct?
Yes, sir. Yes, sir.
So it is not that easy to, you know, plot the curve over in this in a simple fashion. So this is one reason why we, prefer a logarithmic scale. There are other reasons too. One, you have already told, the scale, you have to plot a large number of values in a small scale. That is another reason. There is another reason that, if you look at any standard book, you'll see that they are taking each term, they are calculating the corner frequency, and near about corner frequency, this asymptotic Bode plot holds true. And this concept I have explained in the previous session. That is not not this session. Not in phase 2. In phase 1, there was a one class where I have taught asymptotic Bode plot. So in that class, I have told you how we are actually plotting, how we are getting this asymptotic Bode plot. These asymptotic Bode plots are close. They are close to the real Bode plot only near the corner frequency, not away from the corner frequency. Okay. To the right of the contour. Very very far away from the corner frequency. The asymptotic Bode plots are correct. Not what should I say? Not very close to the corner frequency. I did a mistake over that.
Yes,
So
sir. There was an
yeah,
error according to
yeah,
the.
yeah. So very far away from the corner frequency, the asymptotic Bode plots are correct. So when I'm saying asymptotic, it means omega tends to infinity. So at those frequencies, this Bode plot and the actual Bode plot and the asymptotic Bode plot would match. But near the corner frequency or to the left of the corner frequency, you will find that the two plots may not match. Okay, so these are kind of approximation that we do, and this holds pretty good. Anyways, so if you look at the equation of the line now, let us write the equation of the line. So it has been told that the y-axis is in dB. Okay, it is a gain in dB. It's not just the magnitude. So 20 log mod of g of s, because if mod of g of s is the gain of the transfer function, then 20 log mod of g of s is the gain of the transfer function in dB. So this is the y-axis. So this is my y-axis. Now the slope I have already found out, that is minus 40. So minus 40 into what is the x-axis over here? Log of omega, because the x-axis is in logarithmic scale, plus 32. Why 32? Because the intercept, the y-intercept is 32. So you see, this is nothing but the equation of a straight line, y equal to mx plus c. Do you agree with me, everyone?
Yes, sir.
Is it clear to everybody? Is it clear to everybody? Okay. Okay, good. So if this is the case, now nothing much is left. A bit of mathematical manipulation is required. So, so what I have done over here, I have divided both sides by 20. So minus 2, 40 becomes minus 2, and over here 32 becomes 1.6. Now a bit more of mathematics. So minus 2 over here, we can raise that to the power of omega. So log of omega whole to the power minus 2 plus 1.6 is into 1. So log of 10 is 1. So we can write 1.6 into log of 10. The reason for doing so is because on the left hand side we have log. I want the entire term in logarithmic, in log term. So what I have done is I have written the equation in such a fashion so that I can club the entire thing in the log function, inside a log function. So log of mod of g of s becomes equal to log of 10 whole to the power 1.6 divided by omega square. Okay, so that means mod of g of s is nothing but 39.8 by omega square. So g of s is 39.8 divided by s square. Is the solution clear to everybody?
Yes, sir.
Amruta, is it clear to you? Okay. Anu says it's clear. What about Amruta? You can just type in the type in the chat window. Okay, Lord. So let us not wait for her reply. I don't know whether she's going to reply. So let us just go ahead for the next sum. Okay, the next question is this one. So a bit of power electronics. So an SCR has been given to you, silicon controlled rectifier, and it has been told to you that the latching current of SCR is 40 milliampere. Okay, and it has been told that the gate pulse that has been applied to a SCR is 50 microseconds. So a gate pulse of 50 microsecond is being applied to the gate terminal of the SCR. So you are asked to find the minimum value of R. This is the R I'm talking about. So what is the minimum value of R which is required for successful firing of the SCR? So that is the question that has been asked to you. Again, I will give you 5 minutes time. So and then try it for yourself, and then I'll be asking you questions after this 5 minutes of time, 3 minutes of time. So 21. So I will give 20 up to 20, 7:24. I will be giving you time to solve the question. If anybody has solved the question, just unmute yourself and just say what answer you are getting. . Anybody with the answer yet?
No, sir.
What is the problem in the question that you are facing, Navkirti?
Sir, I just can't figure out how to find the value of R. One thing that I'm getting to know from this question is that a current is given, so we just need it. SCR need to be just forward biased, and I don't know what to do with the data given of gate pulse.
Okay, so what is the latching current? Do you know what latching current is?
Yes, sir.
So what is the latching current? Okay, we will discuss
Sir,
that.
it is the
Okay, we'll discuss it. Okay, let us discuss it. So let me just ask you, how do you turn on a SCR? Just tell me how you are turning on an SCR.
so firstly it's need to be forward biased and then gate pulse is required.
So in this circuit, do you see that SCR is forward biased?
Yes, as a 100 volt is given, so we just need to find the voltage at the other end. So that's what I was not able to find.
Okay. So after it is forward biased, then what do you do?
We need to apply gate pulse.
So gate pulse. So is it a pulse, or do you need to apply a constant gate voltage?
So at every site, we just need to apply once gate pulse.
Why do you do that?
Because after that, it is already in forward conduction mode.
Okay, it is in conduction mode. So if I keep on, if I keep a, if I continue to apply a pulse, what is the problem that you are going to face? Is there any problem that
So,
you are going to face, or is it just
so maybe losses because of that pulse.
correct? Correct, absolutely. In the gate circuitry, see, in most of the questions that you solve in your undergraduate level, the gate circuitry is never shown to you. Okay, maybe there is one question on gate driver in gate examination 2014 or something. I forgot the year on which in which it appeared, but there is a question in which the gate circuitry was given, and you are asked to find something that they have asked you to do. So that gate circuitry is hidden in the power circuit. That gate circuitry is assumed that only a pulse is being provided over here, and the circuitry which produces the pulse is not shown in the circuit. I mean, in undergraduate level, nowhere it will be shown. So what we do is we apply a pulse and then we turn it off, because once the SCR is in conduction mode, or it is shorted, you can apply, you can think it to be ideal switch, and you say that it is shorted, then there is no need for us to apply the gate pulse continuously. Okay, so how to turn off the SCR then?
Sir, there are different circuits like to turn off SCR.
So if I apply a negative gate pulse, would this be turned off or no?
Sir, negative gate pulse, I don't remember, but if we apply negative voltage across it, it will be turned off, but losses will be very high because we need to apply very high reverse bias
I am talking
voltage.
about the control to gate terminal. So if I apply a negative gate pulse at this point at the gate terminal over here, would the SCR be turned off or no?
So maybe no.
Exactly. It is not. I mean, once it is in conduction mode, it is not in our control anymore. So once it starts conduction, you need extra commutation circuitry to turn off the SCR. Okay, so those are outdated circuits. I mean, SCR is hardly used these days. Most people use MOSFETs. So in olden days, external commutation circuit has to be used to to reduce the current flowing through the SCR. So these are latching current, which is required, which information is required for you to turn on. There is another information in the data sheet of an SCR. There is the holding current. So the motive of the commutation circuitry is to reduce the current flowing through the SCR below the holding current. So if it is below the holding current, then it will be turned off. Okay.
Yes, sir.
Okay, so now let us look at the VI characteristics. Okay, we'll understand this VI characteristics because this understanding VI characteristics is very important on the perspective of a engineer, because while you will be working in your labs, you will not find all these textbooks and all those things for the device that you are using. Only thing that you would be left with is the data sheet of the device that you are using, and data sheet what is available to you is this VI characteristics. From there you have to interpret what you need to do. So before going to the VI characteristics, first let us talk a bit about latching current. So as you already know, this is a circuit symbol for thyristor or SCR, that is silicon control rectifier. This is the anode terminal, this is a cathode terminal, this is a gate terminal, and the current through it is indicated by IT. So IT I have written over here. Okay. So another thing that you already know, I think, that the thyristor is capable of blocking voltage of either polarity. So if the voltage is of polarity as shown in the circuit, it can block the voltage. That is, it will be operating as an open circuit. It will be acting as an open circuit for a voltage polarity as shown in circuit, or it may also act as an open circuit when the voltage polarity is opposite. Okay, these are the certain properties of SCR that you must keep in mind. So what is the latching current? It is the minimum current required to maintain the thyristor in the on state immediately after switching it on from off state. Okay, and the triggering signal has been removed. That is why I asked you whether we need a constant signal or a pulsating signal. So once the pulse has been removed, the current to thyristor must reach the latching current for the thyristor to be successfully turned on. If you apply the gate pulse and the current through the thyristor has not yet reached the latching current, then it will again turn off. So successful turning on of the SCR would be failed. You will fail in turning on the thyristor. Okay. So what is happening in this VI characteristics? Let us understand. So this blue curve that you see over here is the VI characteristics. Say initially I am not applying any gate pulse. So Ig equal to 0. So it is blocking a voltage VB0, and we are at this point. At this point on which the cursor is placed right now. Okay. So now let us slightly increase the gate current. Slightly increase the current to this gate terminal. Okay. We're slightly increasing it. So I have increased it to Ig1. So what will happen? We'll move from this operating point to this operating point. Is it clear up to this?
Yes, sir.
So follow this dotted yellow line, dotted chrome yellow line that you see over here. Follow this chrome yellow line. So the moment we are slightly increasing the gate current, we are moving from this point to this point. Now let us further increase the gate current. So what would happen? We would again move from this point to this point. Okay. Now if we further increase the gate current, what will happen is it will move from this point to this point, and which means that it is starting to behave in the starting to go in the conduction mode. That is, the voltage drop across it has reduced to a great extent. Okay, you can see the voltage drop from this curve. So this is not drawn to the scale, but this would be very low value. So after reaching this point, if the current has not reached this value, this end point of the dotted yellow line, if it has not reached this point is the latching current. If the current with thyristor, that is IT, has not reached this current, then it will again turn off. It will again move to this operating point. Okay. So as an engineer, while you design a circuit, you must ensure for successful turn on of the thyristor, after the gate pulse has been removed, the current through the thyristor must reach the value of the latching current at least. It may be more than that, but at least it has to reach the value of the latching current which has been given to you in the data sheet. Okay, now let us see how to solve the sum. Okay, so you see, look at the circuit that has been given to us. The two information that has been given to us is written over here. So latching current, that is written by I suffix latch, is 40 milliampere. It has been given to us. The pulse that we are applying has a period of 50, the pulse width is of 50 microsecond. And now let us look at the circuit. So what is the significance of this circuit? You see, the current which is flowing through the SCR, that is denoted by IT, is divided into two parts, IL and IR. Now, if I look at the current IR, you see, if you consider the loop, which is indicated by the cursor over here, if you consider this loop, it is nothing but a resistive circuit, right? It is only a R resistance which is connected across 10 volt, a 100 volt, right?
Yes, sir.
So this current IR is not going to show you any dynamics. It's a resistive circuit, so no dynamics. It will not be showing any dynamics. So the value of current IR would be 100 divided by R, right?
Yes, sir.
Now what about the current IL, that is the current flowing through this inductor? Will it show any dynamics?
Yes, sir. RL circuit.
Yes, it is nothing but a RL circuit. If you consider this loop, it is a RL circuit. So let us write the equation for this inductor current. So for a first order system, I think you are very much conversant as of, so the time has already passed for your gate. It is already the end of the year. I am quite sure that you are quite conversant in writing these equations. So you know this is the final value. What is final value? That is at t equal to infinity, inductor will act as short circuit. So we can say that t equal to infinity, the final value of this inductor current will be 100 by 500, 100 by 500. So 100, and the inductor is acting as a short circuit. So 100 by 500 is the current at t equal to infinity. Okay. 1 minus e to the power minus r by l into t. Okay. R is 500 ohms and the L is 200 millihenry. So that is the time constant, the inverse of the time constant that I have written over here. Okay. Minus r by l into t. So what you are interested to find is what value this current IL would reach to after you apply the gate pulse. Okay. The pulse width is of 50 microsecond. So let us see what the value of IL would be after this 50 microsecond has passed. So if I put t equal to 50 microseconds in this equation, we'll find that the value of IL would be 0.0235 ampere. Okay. What does that mean? There is 23.5 milliampere. Correct?
Yes, sir.
So you see this IL value is less than the latching current. Do you get that? It is less than the latching current, that is 40 milliampere. Correct?
Yes, sir.
So you must ensure that the current IR which is flowing through this branch must be the excess amount of current that we require. That is the amount. So 40 milliampere minus 23.5 milliampere is the excess amount of current that must be there at the point when the pulse has been removed. So the current which is flowing through this resistance R must at least be a value of 40 milliampere minus of this value, that is 23.5 milliampere. This is what I have done. So I have again written that IT is equal to IL plus IR, and we want the value of IT to reach 40 milliampere after a period of 50 microsecond, and we have seen that IL has already reached to a value of 23 milliampere. So IR must be 16.5 milliampere or 0.0165 ampere. So if this is the value of the current which we want to flow in this branch, what would be the value of R? That is nothing but 100 is the voltage across this resistance divided by the current which we have already found. So the value of resistance would be 6060.60 ohms. Is the solution clear to everybody?
Yes, sir.
Did you understand the philosophy of the question that what has been asked to you?
Yes, sir.
Okay. Anu, is it clear to you? Okay. Good. Okay, it is already 7:44. Do you, Navkirti, you have missed the previous class. Do you want me to, repeat the questions that I have just, that we have talked about in the previous class? Anu, if you want to stay, you can stay. I would be discussing the questions that I've discussed in the previous class one more time because the attendance was very low. Even today, the attendance is very low. But let us still discuss. Do you want to try out this sum, Navkirti?
Yes, sir.
Okay, so this is a full bridge rectifier circuit that you can see in the diagram over here, and there's a capacitor placed across it, and there is a Zener diode as you can see over here. So what has been asked to you is, considering all possible values of RL, what value of RS you must choose so that the Zener diode does not burn out. Okay, that is the question that has been asked in the that asked in the gate question. So try to solve it and tell me how you are going to solve it. So I'll give you 2 minutes time to solve. It's from mentally also you can do it. It's very simple sum, but still. So are you done with the sum, uh, Navkirti?
No, sir.
Just tell me the approach you are taking for it.
Sir, I was just trying to find currents, value of current in the circuit, like considering just positive half and.
How are you doing it?
So, like, Zener diode is 5 volt and 0.25 volt given, so maximum I can be 0.05.
Right.
So, because of that, so current in RL branch I need to find, and for that voltage is given 20 that 20 divided by under root 2, for which the circuit for, if we can I consider the positive half, it will be RS plus RL in that equation, and from that I was
So
trying to
what
get
is?
it.
Can you tell me when the current through this would be maximum? When will be the current through the Zener diode maximum? Just tell me this condition. If you can identify this condition, this sum would be over in no minutes.
So
Okay.
when
Yes. When?
almost when it's short circuit in a kind that then
If,
only
what is short circuited?
it will be in conduction.
So if this is short circuited, then the entire current to flow through this branch, right? If the load is short circuited, then the entire current will flow through the load when through
Yes.
this path which is shorted, not through the diode.
Okay, sir.
So if I short these two terminals, then the entire current will flow through this shorted path. No current will be flowing through this Zener diode.
Yes,
So
sir.
when will be the current flowing through it the maximum? It is when it is
So
open circuited. When RL is open circuited, just let us look at the the basic shunt circuit. These are basic shunt circuit. Okay. So what this Zener diode does is it maintains a constant voltage Vz, right?
yes, sir.
So if it's maintain a constant voltage and you have Vi, now this Vi is not constant. This is something which is not constant. Okay. This unregulated voltage. Okay. This may be varying. So to maintain a constant voltage across the load, you connect a Zener diode across it and you connect a resistance in series so that the excess voltage, that is Vi minus Vz, is dropped across this resistance Rs. Correct? This resistance is very important, and choosing this resistance is really very important in any in the design of a shunt, a linear shunt circuit. This is a very common question where you have to determine the value of this series resistance Rs. Okay. So if that is the case, now say if I now look at this current I in. So this current I in is again divided into two parts, Iz and IL. Okay. So when there is a load connected across these 2 points, the current I in will be divided into two parts. One is the Zener current Iz and the other is the load current IL. Now under lightly loaded condition, that is when RL is very high, or when it is no load condition, that is RL is completely open, the entire current I in will be flowing through this Zener diode, right?
Yes, sir.
There will be no other path for the current to flow. It will be entirely flowing through this Zener diode. Now, what you need to identify is when is this IN maximum? And the maximum value of IN should not exceed the rated value of IZ, or the Zener diode, rated current of the Zener diode, which I have found out to be 0.05 ampere, as you have already told me. This is something we have to ensure.
Yes,
So
sir.
when do you think it will be maximum IN?
So at peak of Vi.
So what you get across this capacitor, the voltage across the capacitor filter is the average voltage, right? Average voltage of the unfiltered voltage waveform. Let us look at the waveforms. Okay, so this dotted black line is the unfiltered output voltage waveform of a full bridge rectifier, correct?
Yes, sir.
And what is this beta minus alpha interval that I have drawn over here? Can you tell me what is this beta minus alpha interval? Why have I marked with beta minus alpha? What happens in this interval?
Sir, at alpha there will be we will fire the SCRs.
SCR, there is diodes over here.
Yes, sir. Sir. Oh, sorry, sir.
So what is happening at alpha and what is happening at beta? At alpha, the diode starts conducting. Please keep in mind the waveform that I am showing you is the steady state waveform. It is not the waveform when the rectifier is starting. It is at this steady state condition when this waveform is valid. I was asked to, I was about to ask you this question, but because of lack of time, I'm just mentioning it to you. The waveform that you see is the steady state waveform. It is not transient, or it is not the startup waveform. Okay. So at steady state, what would happen is, at point alpha, the diode will be forward biased, and this beta minus alpha is the conduction angle. During this period, the diode will be conducting. Okay.
Yes, sir.
And beyond this beta, the diode would be reverse biased, and the capacitor will be discharging through the resistance. That is, the capacitor will be considered this entire thing as a load. So after beta, the diode will be reverse biased, because the capacitor voltage would be higher than the input, the voltage, this VIN voltage, and as a result of which, the diodes will be reverse biased, and the capacitor will be discharging to the load resistance. Okay, consider the entire thing as a load resistance. So when do you think would this blue solid line would be very close to the peak value? When do you think it will be very close to the peak value?
Just after the diodes are reversed bias, getting reversed bias.
No, I'm not talking about that. See, the average value is something like this, right?
Yes, sir.
The average value is as shown by the flow of the cursor on the screen. You see the flow of the cursor on the screen?
Yes, sir.
This is the average value that you are getting. So
Yes, sir.
when is the average value very close to the peak value?
Sir, beta.
Not at beta. When the load resistance is very high, or under lightly loaded condition, or no load condition. In such a case, you see the capacitor has no path to discharge. If the load resistance is very high, or there is no load, if you consider the circuit and you say that you have open circuit the entire stuff, you have only a capacitor across it, then there is no path for the capacitor to discharge, right?
Yes, sir.
So if that is the case, it would, the capacitor, if you are operating at no load condition, the capacitor will be charged, and then it will stay put over there, because there is no uh, there is no path for the capacitor to discharge any longer, right? Because the current can only flow in one direction. The current cannot flow in the opposite direction. So the current from the source is flowing in one particular direction, and it is flowing to the capacitor. Once the capacitor is fully charged, when the capacitor voltage across the capacitor is the peak value, then all the diodes after this, say there is a interval beta, after that the capacitor voltage across the capacitor will always be higher than the VIN voltage that is appearing across this, as a result of which the diodes will be reverse bias. The diodes won't be conducting anymore, and the voltage across the capacitor will stay put at the maximum value. Correct?
Yes, sir.
Are you truly getting what I'm saying, or you are not getting, or just
Yes,
saying
sir.
yes?
Yes, sir. Yes, sir. I'm getting it.
Okay. So what would happen, yeah, if you normally, if I'm giving a just a brief, a very rough thing I'm saying, say it is just charging up to this value, and then it will step put at this value, at the peak value. Correct?
Yes, sir.
So at very, when the load resistance very high, or at lightly loaded condition, the average value across the capacitor would be very close to the peak value. So that is my worst case condition. I would ask you a few more questions on in a in a full bridge rectifier, but before that, let us solve the sum. So 20 volt is the peak value. So let us consider 20 volt as the worst case condition. So I'm saying that 20 volt is across this capacitor, and the diode, the Zener diode is maintaining a voltage 5 volt across it. So, and I want the current under the worst case condition to be 0.05, which is the rated Zener current. I do not want the current to exceed this value. So I know the potential at this point, I know the potential at this point, and I know what current I want to flow through this resistance Rs. So we can find the value of Rs like this: 20 minus 5 divided by Iz. So that is 300 ohms. Got my point?
Yes, sir.
Okay, now tell me, so in this question, so these are design engineering questions. So when you are designing a circuit, you must ensure whatever components that you are using, the maybe the diodes, this diodes, the power diodes that I am showing by my cursor, and the Zener diode, they shouldn't burn out. Even under worst case condition, they shouldn't burn out. In the question, It has been specified to you that they are concerned only about this xenon diode. What about this diode? What about this diodes over here? So, is there any possibility that this diode may also burn out? Can you tell me at what condition this diode may burn out? Anu, can you tell me at what condition they condition the diodes, the power diodes may burn out?
Sir, if
Yes.
voltage is exceeded, then that breakover volt.
Say you have taken into consideration everything. Okay, everything you have taken into consideration. You have seen that the voltage across this is not above the peak inverse voltage. You have all maintained all those relation, and you have built the circuit. Now if you build the circuit in the lab and if you test it, will this work or it will not work?
Sir, can you repeat the question?
I'm saying that you just said that if the voltage across the diode increase above the peak inverse voltage and all, so you have made all those calculations and you have made the exact circuit of the full bridge rectifier as shown by the blue block on the screen. Okay, the circuit that I am worried about right now is indicated by the blue box that I just show on the cut that I'm showing on the cut on the screen. So I'm concerned only about the full bridge rectifier over here. So what I am asking is, so if we consider only this circuit and if you build the circuit in your laboratory, will this work or there may be a condition where this circuit may fail?
So the only condition left is, as you said, voltage is not. We just took care of voltage, so current is left. We just need to.
So what condition I mean do you think would may lead to the burning out of the diode? Anu, can you tell? Do you have any idea? This less load is for which, Anu? Okay. So do you have any idea when this circuit that you have just built, a simple, full bridge rectifier, which you have been studying from your third year or second year? So will this work? The circuit that I just showed you, will this work, or is there any chance that circuit would burn out? This is a circuit that you have seen in all your, all your standard books, textbooks. What do you think? Will it work, or is there some modification required? Just say if burn out. Why? When will it burn out? Why do you think it is going to burn out? I mean, this is a circuit that you have seen in all your textbooks, right? In all your textbooks from your bachelor level, even in your masters, if you have done masters, you have seen extensively this full bridge rectifier circuit. Now you are saying that it may burn out. Why do you think it will burn out? Okay, so let me just briefly tell. So you see, in the textbooks, something is assumed that you already know. Say there is a switch over here. Okay, there is a switch at this point on which I mean the point on which I have made the block. Say there is a switch over here. Now the moment you turn on the switch, there is a a single pole double throw switch, or a single pole single throw switch, not a single pole double throw, single pole single throw switch. So if there is a single pole single throw switch, that is there is a manual switch over here, and you turn this on. During starting, the capacitor is totally discharged. The voltage across the capacitor is zero. Correct?
Yes, sir.
So now if you turn on the switch, what you are actually doing is you are actually shorting these 2 points. Correct?
Yes, sir.
So what would happen is it will burn away. So as you short these 2 points and you turn on the switch at the point when the voltage is not at zero. So when you are switching on, you don't know what is the voltage at this point. Say at t equal to 5 milliseconds, you are turning it on. So at t equal to 5 milliseconds, you do not know what is the magnitude of the voltage of this sinusoidal waveform. So maybe you are turning at this point. You are turning on at this point. So if you are turning on at this point, then the voltage, the VIN has a maximum value. Vi is a maximum value and you have shorted the load terminals. So a huge current will be flowing. Correct?
Yes, sir.
You got my point?
Yes, sir.
Now you can clearly understand, clearly explain why. Can we explain it to somebody else? Why this
Yes.
may be a problem?
Yes, sir.
So when you are turning on the switch, you do not know at what instant you are turning on. So if you do not know what one instant you are turning on, it may so happen that when the voltage of this Vi is at its maximum value, you are turning on, and the capacitor is discharged, the capacitor is not charged. So a huge current would be flowing through the capacitor, and it may burn out the diodes that you are using. So what is the remedy for it? So there must be something. So what remedy do you suggest? What can we do to limit this current?
So to use a charged capacitor,
Okay, that is one solution. Anything else? So what you are saying is we need another external circuit which would charge the capacitor beforehand before we turn on the switch. Correct?
yes, sir.
Okay, so that is one solution. That may be one solution. Any simpler, low cost solution that you suggest?
So using inductor,
Using an inductor. So won't
no,
that
sir.
lead to? Yes, go
No,
ahead.
sir.
Okay. So another simple suggestion, or another simple remedy, low cost solution would be, connecting a resistance in series with the source. You connect a limiting resistance in series with the source and let the capacitor charge. Once it is fully charged, you short those resistance. Right? You got the point. So I'm putting
Yes,
a
sir.
resistance in series with the voltage source at this point where I've made the block, and connect a switch parallel to it. The moment the capacitor is fully charged and it has gone into steady state, we'll turn on the switch in parallel with the limiting resistance, so that we do not have much of the losses and we are going to get the volt that we want. That is one thing. Any other solution that you can suggest? Another solution would be, connecting a thermistor. The thermistor is a resistance whose value is temperature dependent. So as temperature rises, a negative temperature coefficient. So as the current keeps on flowing, as it goes into a full loaded condition, the current through it would be becoming high, and the resistance would drop, and ultimately it will go to zero, and it will be acting as a short circuit. So if you connect a thermistor having a negative temperature coefficient in series with the uh, voltage source, sinusoidal voltage source that you see on the screen, then also you do not need an external switch to short the limiting resistance. Rather, the resistance itself would be tending to lower values as the temperature across it rises when the current through it rises. So that is another solution. So another question that I asked Anu in the previous class is, how can we find this alpha and beta? Do you have any idea how to find this alpha and beta?
Sir, usually alpha is 30 degree.
No, there is nothing called usual. What do you mean by usual?
So I was just drawing those waveforms for like three phase, and so I just remember from that.
No, no, those are, I mean, that is entirely different thing from this. I'm not talking about those. It is not that easy to find alpha and beta over here. Okay, you need to solve, transcendental equations to find alpha and beta. Uh, so after your gate and all these things are over, you can ponder over it how to find alpha and beta. This is one of our assignments when we do course over here. This is one of our assignments. This is in the first two class. You would be asked to find the value of alpha and beta. Okay, so I mean, if I mean this, even this single phase rectifier itself is such a big topic that has been that is taught extensively in the entire semester. It will be taught this a single bridge, this full bridge rectifier. So there are several aspects to it. I mean, if I start talking about each and every aspect, it would take the entire semester to complete. But yeah, uh, so another question that I would like to pose: what do you think would be the value of beta? This is the question I asked Anu in the previous class. What do you think would be the value of beta?
So 90 degree.
Yeah, in most of the books you would find it is 90-degree, but is it so? Are they assuming something, or it is always 90-degree? What do you think?
So should it depend on how capacitor is discharging?
It will depend on it. So it is depending on what value?
So capacitance.
It will depend on the time constant. You see, this is the dotted waveform is the rectified VI waveform that you are seeing on the screen. The blue waveform that you see is the capacitor discharge waveform. Okay, so when the capacitor discharge waveform is higher than this dotted waveform, then you know the diode will be reverse biased and the diodes will not be conducting. If the resistance is low, now you may ask how low is low. So the the thing that you have to ensure is the time period. If the half of the time, so time constant of the circuit is much higher than the half of the time period of the signal that of the source that you are using, then this kind of waveform is true. That is, if your load resistance, maybe your load resistance is very high, in that case the time constant formed by the capacitor and the resistance, the R into C value, is much higher as compared to this T by 2. Say this is T by 2, this is T, and then again this is 3T by 2. Okay, so this time constant, the time constant of the discharge of the capacitor, the discharge circuit of the capacitor, must be much higher as compared to almost 10 times or 100 times or something like that. If that is much higher as compared to the time period of this of the source voltage that you are using, then I can say that this waveform is true. If it is not so, if the condition is not so, that is, if the time constant of the discharge circuit of the capacitor is much lower as compared to the T by 2 value, then what do you think would be the value of beta? Would it be less than 90 or more than 90?
So more than 90.
Right, because you see, the slope of the blue curve is, that would be your time constant. Okay, so if the time constant is low, then the slope would be, I mean, if your time constant is much lower, then the slope would be far more higher. I mean, oh, I cannot draw over here. Okay, so this would not be the slope, rather the slope would be much steeper like this. You follow the cursor over here. So if the time constant is much lower, that is the value of R is low, or the C is high, I mean the C is low. Sorry. I mean R into C, right? So if the value of the time constant is low, then the discharge waveform of the capacitor will not be like this. It would be far more steeper like this, right? It would be discharging very fast as the resistance is very low, right? Getting my point?
Yes, sir.
So if it is discharging very fast, then this dotted waveform that you see would be above this blue waveform, right?
Yes, sir.
So it is discharging very fast with the slope as shown by the flow of the cursor on the screen. But it is discharging very fast. Then you see all these points, all these points, this dotted waveform would be higher than this discharge waveform. And the period for which this is higher, during this entire period for which this dotted waveform is higher than this discharge waveform, the diodes will be conducting in. So beta would be higher than 90 in that case. Clear?
Yes, sir.
Anu, is it clear? This is a question I think I asked you in the previous class. Okay. Good, good. Okay, it is already 8:16. Okay, I would put an end to the class today, and we would be meeting again on next Friday. Okay, we'll be meeting again next Friday. The today's class went long because I discussed this single phase rectifier and all. Next class won't be more than 30 minutes. Okay, I'm really sorry because of this long class. Okay,
No, sir. Thank you.
thank you very much. Thank you. Okay, bye bye then. Enjoy your weekends.